Hi, this is David. I thought it'd be fun to take a concept that we study in the FRM and apply it to a puzzle in the real world. In this case, the news is that Elon Musk is purchasing Twitter, or at least he was until he held the deal up until he investigates their claim about bots on the platform. Bots are fake accounts. Twitter says that only 5% of their accounts are fake. And Elon Musk said, okay, I'm going to check that by randomly sampling 100 accounts. I don't know why he picked such a small sample. That's what I read. Maybe when they do it, they'll pick a larger sample, but let's use his number there of 100. This lends itself to the binomial distribution, which I have plotted here, which is a fabulous and useful distribution for the same reason that we use it in the FRM. In the FRM, we use it to back test value at risk, right? We use it for a VAR back test, but it's useful in both cases. Why? Because when Elon Musk goes to look at each account, it's probably going to be a real person, but it might be a fake bot. That's a classic either or, right? Is it a bot? Yes or no, true or false. That is a Bernoulli variable, we call that, the simplest possible random variable. And if we have a series of Bernoullis or a set of Bernoullis, then that is described or characterized by a binomial distribution if it's true that they are IID. Always like to remind our folks that we need that IID assumption, that's independent and identically distributed random variable. Common assumption in finance that's or commonly assumed. We need our Bernoullis to be IID, and then we have a binomial. So what does that mean? Well, that means, the independence in this case is the more important one, I think. And that is to say, if the sample's not really random, let's say it clusters somehow due to the procedure, then we don't have the IID, right? So any kind of clustering or autocorrelation would be a violation of that independence. But if we have these Bernoullis, yes, no, bot or not, bot or human, one or the other, and they are IID, so we really have a random sample, then it's fit with a binomial distribution that I've plotted here. And what I've plotted here on the right is the same column that's showing over here. So this first, in this bar chart, this first bar here with the 0 is the 0.59%. It's less than 1%. This next one, the probability of one fake out of 100 sampled is 3.12%. So you can see here, I just used Excel's binom.dist, which retrieves that probability for me. And it's just taking really 4 parameters here. The number, that's the 0. So it's the probability that we observe 0 fakes among a trial or sample of 100. That's the probability of exactly 0 in a set of 100 observations, where the probability of each fake is P here, only 5%. And I just need to indicate, do I want the cumulative distribution function, or do I just want the exact value that's plotted here, the probability mass function? It's a PMF or a PDF. A PMF is correct because this is a discrete distribution. So you can see that gives me the 0.59%, and cumulatively I have the same value. I could have gotten this 0.59% also by taking 95% raised to the 100 power, because that would be the cumulative probability of a real person, a real person, a real person, 100 consecutive times in a row, right, is 95% to the 100 power, is also the probability of exactly 0 fakes among the 100. But then after that, we got to use the binomial distribution. But you can see cumulatively, when I get down here to 3, the probability of exactly 3 fakes among a sample of 100 is almost 14%, and then cumulatively it's 25.78, which is the sum of all of these. So when he goes out to sample 100, the mean of this distribution is here at 5. The probability of observing exactly 5 fakes out of 100 is the mean of the distribution but it's only 18%. It's this bar here. It's a little bit higher than the 4 you can see. So sampling variation is very important, especially when the sample is small relative to the population, as this is the case. That means that we could have a good sample or a bad sample. Samples will vary. The mean of each sample will vary. So probably, if you agree with me or my intuition, if Elon Musk goes out to sample 100 accounts and he finds 4 bots out of 100, which is 4% of the sample, or 6 bots, which is 6%, we could probably still find it agreeable that Twitter's claim of 5% or less is true. After all, we're pretty close to 5, and you can see conditional on the 5% being true, that we've got here some dispersion in this distribution. What about 7? If he finds 7 out of 100, that's 7%. Do we accept or reject the claim? Well, you can see here the probability of exactly 7 is 10.6%, and cumulatively, that just means, right, adding up the probability of all of these bars here from 0 to 7, it's only 87.20%, meaning 12.8% over here to the right. 12.8% is quite plausible outcome. So if we want any high confidence level, we're not going to reject 7 fakes out of a sample of 100. So this is just the nature of the statistical decision. We're taking a sample from a population, so we're going to make a decision, or he's going to make a decision based on that sample, and he makes that decision in the vacuum of uncertainty. He can't know whether it's correct or not. It's a matter of how confident does he want to be, and what trade-off does he make between the 2 errors, his type 1 and his type 2 error. So an interesting thing about this claim, though, I will say, is that our default assumption when we do a statistical test, we usually do a 2-sided null. In this case, though, it would be a 1-sided null that's appropriate, right? The null, what is the null hypothesis? The null hypothesis, to me, is that the true mean of the population is less than or equal to 5%. And the alternative is that it's greater than 5%. And so you see why I say it's one-sided, because if Twitter's claim, let's just say Twitter's claim is 5%, the null does need to anchor on an equals, so 5%. But if they're wrong and it's really only 4, then Elon Musk doesn't care. That's not bad. He cares about more than 5% bots. So I say that's a one-sided test where the null hypothesis is 5% or less. And the test is then, are we going to reject that null, or are we going to accept it? And then by accept it, we really mean fail to reject it, right? If he rejects that null, then he disputes, he does not believe their claim. And so then it becomes a question of selecting a cutoff. Now, and what's our confidence? So typical confidence levels are 95% or higher, maybe 99, but let's use 95% as our confidence level. And we can see over here on the cumulative distribution function, if I go down to 8 fakes, the cumulative is 93.69. And so if I set a cutoff of 9, then I can just take 1 minus, I have to go up here to get 6.31, and I'm going to copy this down. So if I choose a cutoff of 9 or greater, then the area in my right tail is going to be 6.31, right? That's because 8 or less is 93.69. 9 or greater is the area in the right tail. 6.31% is not a low enough significance in practice. Typically, we need 95 or more. And so let's go down to 10 or more cutoffs, and let's draw it there, because the area to the right tail is only 2.82%. So we're going to get greater than 95% confidence, but we have a discrete distribution and there are some subtleties here in our selection and actually some choices that I'm not going to get into. What I am going to do is draw the cutoff here at 10, just to show you that if we say, if we observe the probability of 9 or fewer fakes or bots among 100 is 97.18%, then the probability of 10 or more is the area in this tail, which is 2.82%. And so I'm going to select that as the cutoff. And then this is going to be the probability, okay, I'm running into my area a little bit, of a type 1 error. That is what I mean by that is that's going to be 2.82%. If a cutoff of 10 or more, meaning let's say we observe he runs this 100, he finds 10 fake accounts among 100, which is 10%. It's twice the 5%. So already intuitively it looks bad, right? But and so it's at our cutoff. We are going to advise Elon Musk to reject the null hypothesis in favor of the alternative. In other words, we find their claim to be false. However, we do still risk a 2.82% probability of a type 1 error, which is to say we run the risk of rejecting a null hypothesis that in fact was true, because you can see it's possible. It sort of stretches the imagination. They say 5, we got 10 on the sample, but sampling variation does allow for the possibility, and it's not infinitesimal. It's quite plausible. But if we want 95% confidence, that's where we're going to that's where we're going to set the cutoff. We're going to run the risk of a type 1. If we don't like that, if that's too high, we can set this cutoff higher, but we do face the trade-off. What's the trade-off? Well, let's go back to our cutoff here of 10 or more. What happens if Elon Musk finds 9? He observes 9 fake accounts out of 100. That's 9%, but it's below the cutoff. So he fails to reject the null, barely. In other words, accepts the null, accepts the claim as valid. He is now risking a type 2 error, which is to say he is accepted. The error would be he's made a decision to accept the null when in fact the null, unbeknownst to him, is false. Right? So, and you can see maybe they have the actual amount is 9%. The actual number of bots on the platform is 9%. He observes 9. Well, that's the mean. So that's a completely plausible outcome. But in that case, it's barely under the cutoff because of the decision trade-off. He accepts the null, but the null was false, and he's committed a type 2 error. So it's a trade-off as to where we do this cutoff, which kind of error we have, and the cost of each error. One other thing I will show you is the normal approximation. So, and that is to say the binomial, as the sample size increases, converges on the normal. So if it's a large sample size, it's okay to approximate the binomial with the normal. And here I've repeated my parameters: 5% probability, 100 trial. The expected number of fake accounts is 5. And the standard deviation here is just the standard deviation of it's really just a Bernoulli variable, 5% times. Well, the standard deviation of the Bernoulli is 5% times 1 minus 5%, and we take the square root of that, we get the standard deviation of the Bernoulli. And if we include the 100 in there, we get the standard deviation of the binomial distribution under that IID assumption, which is 2.18. That would be a counts because we've included the 100. And then we go to approximate and we have the normal. And what's the rule for that? Well, the binomial has skew to it. And so the rule, normal approximation is okay. One rule is, the rule I use, is that probability multiplied by sample size is greater than 10, and the same for 1 minus the probability times the sample size greater than 10. Here we've got 5 times 100 is 5. We actually don't have a large enough sample. There's too much skew in the binomial is a way to look at that. And actually it's easy to show how this is directly related to the skew. So we really don't have enough to approximate with the normal, but let's do it anyway. 95% significance. Our normal quantile, one-sided, right? We're going to do a one-sided test, is 1.645. That's very familiar to FRM. And then notice my cutoff, I just simply apply the normal, or I really unstandardize it is what I do. And that is to say, I take the mean and add the standard deviation multiplied by the normal quantile. You can see there gives us 8.58. In other words, on a normal distribution, if we go out 1.645 standard deviations, we get to 8.58. And then here I just round down and round up because after all, we're talking about a discrete distribution. So here under the normal approximation, you see I get 9 for the cutoff, which is right here. The normal approximation would give it to me right here. Here's by my binomial, where I argued previously that the cutoff should be at 10. And I'll probably in the notes explain a little bit more about the theory on that, because I won't be surprised for someone to come along at some point and say it should be 9, or some actually even some interpolation of that. But I'll defend my 10 in the notes. But you can see I do get a different result. Here is the binomial CDF. Here is the normal CDF. So if we now, let's just bump up the number of trials here to 1,000. So probably the last thing I'll do. So if Elon Musk goes to a larger sample size, you can see 50 is the expected. Now my test certainly applies. I have reduced the skew. The skew in the binomial reduces enough that the normal is okay. And now I take the 50 times 1.645 standard deviations, and I get a cutoff here of about 62. So that cutoff would be here, pretty close to where it would be with the binomial. And of course, when I increase the number of trials, I just wanted to show you the normal approximation. But if I go back here, and you can see, as you would expect, an easy we cannot get a free lunch in terms of the type 2, type 1 trade-off. There's no free lunch. The only free lunch here really is increasing the sample size, right? We just looked at Elon Musk's sample of 100, and we found that the cutoff, at least the way I showed you, that cutoff would be 10 against 5, right? So it's fully a factor of 2. Now let's just double the sample size to 200, right? And let me just take this out so you can just see that that's the multiplier, right? The ratio of, we expect 5, our cutoff is 10 or twice that. It's quite a ways out. Now I go to a sample size of 200. Where would I draw the cutoff? Well, I'm going to copy these down. For the 95% cutoff, you can see I would put that cutoff at 16 fakes or greater, right? If we sample size of 200, the null is 5%. That means the mean is, we expect 10 in that case. But if we get 16 or more, then the probability of our type 1 error or our exact significance level is less than 5%. It's 4.44%. So that's where I would draw the cutoff. for a 95% confidence, and that would be at 16 or greater, we would reject the null. And this is just a simple way of looking at it. That ratio, right, is 16 on the 10. And you can see by doubling the sample size, I really really decrease the ratio in terms of my ability to reject. So we do get a free lunch in that sense. And that would just keep coming down as we increase the sample size. So the easiest thing to do there to decrease the probability of both type errors simultaneously is just increase the sample size and be mindful of whether that's truly a random sample and it's truly IID. But I hope that's a fun application of the binomial distribution against this recent event that's in the news. Thank you.